Assalamu alaikum everyone. My name is Bara'ah. I'm from Sultan Qaboos University. Today, me and my partner Sarah are going to present to you our final year project, which is Integrated Optimization of Operations and Energy Planning for Sustainable Industrial System in Oman. Imagine a factory in Oman running 24 hours a day, producing thousands of water bottles every hour. Now imagine this factory is powered almost entirely by fossil fuel, expensive, polluting, and unsustainable. This is not a hypothetical scenario. This is the reality of most industrial facilities in Oman today. And this is exactly where our story begins. This slide shows the content we're going to cover today. Oman currently relies on natural gas for more than 95% of its electricity, while renewable energy contributes only 2.5%. At the same time, industries consume a significant portion of this energy. But here's the challenge. Oman Vision 2040 aims for 30% renewable energy. So the question is, how can industries, not just homes, become part of this solution? While many studies focus on residential and commercial sectors, industrial applications remain largely unexplored, especially in real-world Omani conditions. There is a gap, not in theory, but in real implementation, and our project was designed to close that gap. The picture on the left-hand side shows the typical hybrid renewable energy system configurations addressed in prior studies. Our objectives were: first, understand the factory's current energy use, then design different hybrid renewable energy systems, then find the best one, lowest cost and lowest emissions, then test how sensitive the results are to changes like electricity prices or solar costs, and finally provide a practical roadmap for Omani industries. This flowchart is divided into three parts. The first part is study preparation, where we conducted a literature review, then selected the factory we're going to collaborate with and collected the data we needed for simulation. Then model development and evaluation. We developed a simulation model and did a verification and validation for the model, and then optimized the experiment. Next, for robustness and uncertainty, we conducted a sensitivity analysis, and inshallah, we will continue with our project in doing a Monte Carlo uncertainty analysis. Our case study is Mountain Springs Water Factory in Behla in Al Dakhiliya region in Oman. This photo, the first one on the left-hand side, shows the factory. It produces 24,000 bottles per hour for different sizes like 250 milli, 500 milli, and 1.5 liters. The second picture is the rooftop, about 4,248 square meters available for solar panels. Currently, the factory relies 100% on the grid and pays about 33,000 Omani riyals per year for electricity. Perfect candidate for transformation. Next, we started collecting the data we needed. We contacted the production manager in the factory to verify the tariff implemented there. And it's the industrial tariff table shown on the left-hand side of the slide. We also contacted Nama Company, which is the company responsible for supplying Oman with electricity, and it's run by the government, which is the bulk supply tariff we're going to need for our project. Next, we collected the load data, and the production manager also gave us the monthly load profile data of the factory, and by assumption we converted this data into hourly data. We contacted different hybrid renewable energy companies in Oman like Madad, Nifad, Altic, and Mawarid, and they provided us with the different technical and economic data we need for our project.
Assalamu alaikum everyone, my name is Sarah and I will continue from here. We tested 5 configuration: grid only, PV with grid, PV with grid with battery, PV with grid with diesel generator, and the last one, PV with wind with grid. We used Homer Grid software for the simulation. It is designed for the grid connected hybrid system. The middle figure shows how PV, grid, battery, diesel generator and the wind turbine and the loads are connected in the home or grid. For the analysis, we use the real data for the load, weather, and tariffs. Then we simulated and optimized all the configuration. Finally, we rank them based on the cost and performance to select the best option. Before trusting the result, we verified the model input and validate its behavior. We check load profile, tariff structure, component data, and unit consistency, and compare the model with the grid-only baseline. Then we did a test to the model under extreme scenario. For example, with the very high grid tariffs, the model minimized grid use and shifted to the renewable. And with the very low PV cost, the PV became the domain energy source. In both cases, the model responds logically, confirming its reliability. Finally, validation against real data shows only a 4.6% variance, which reflects system looseness and operational margins. The optimal configuration is PV grid. No battery, no diesel, no wind. The optimal size had the PV capacity of 215 kilowatts and 1061 kilowatt converter. And environmentally, the PV grid system reduced the CO2 emission by 37.33%. The system has the lowest net to present cost, which is $1.04 million, and has the least levelized cost of energy at $0.0778 per kilowatt, and payback period of 9 years. We tested how the change in the factory load profile, electricity purchase tariff, the bulk supply tariff, and the PV capital cost, how will affect the system. First one, the factory load profile sensitivity. If the factory load increases, the PV size grows potentially, which will increase the operating cost and the net present cost. On the other hand, the LCOE reduced, but the payback period remained the same. The second one, if the electricity purchase tariff increased, PV becomes better choice and the net present increase, and the payback period decrease. Number 3, the bulk supply tariff sensitivity. If the bulk supply tariff increased, the system export more energy, and the net to present cost, LCOE, and operating cost, it drops significantly. Number 4, capital cost sensitivity. If the capital cost of the PV increase, which is happening globally, the payback period shorten because the PV system is almost zero. What does the project deliver? For the factory, lower cost and reliable energy. For Oman, support Vision 2040. For the environment, significant emission reduction. This is not just a model, it's a real step toward sustainability. Globally, contribution, it supports SDG 7, 9, 11, 12, and 13. In the conclusion, the optimal configuration is PV grid with 250 kilowatt solar. It supplies 38.5% of the energy from the sun and reduces the emission by 37% and payback period in 9 years. The system is technically feasible, economically viable, and environmentally beneficial. To conclude, our findings offer practical steps for the future. For the industry, use a proper design, phase implementation, and match system to the actual load. For the policymaker, offer intensive like a higher sellback tariff to accelerate adoption. For the researcher, use a higher resolution data, load data, and the Monte Carlo simulation for uncertainty analysis. This project offers useful guidance for industry, policymaker, and researcher in Oman. Thank you for listening, and we hope our project inspired you.